Hello everyone, my name is Haosen Shi. I'm very glad to present our work, Deep Multitask Learning with Progressive Parameter Sharing. Modern deep learning models in computer vision can match or even surpass human beings. However, some tasks such as autonomous driving require multiple vision tasks to be completed simultaneously, which poses a huge challenge to computing resources. The idea of using a single model to perform multiple tasks is called multitask learning. The objective of multitask learning is to use fewer parameters while keeping the average performance among all tasks. To save resources as much as possible, one common approach to deep multitask learning is to use a shared neural network called the shared backbone to learn shared features, and then use separate specific neural networks for each task to handle the difference. Compared with training single-task models for each task, multitask learning effectively saves parameters. However, the performance of some tasks training together will be hurt. This phenomenon is called negative transfer. How to solve negative transfer is the main challenge of multitask learning. To achieve the objective, the core is to avoid the task's interference on shared parameters. Recent works have proposed many methods to solve this problem, which can be roughly divided into two categories. The first is to improve the architectural design of the multitask learning model, which requires high-level human expertise and rich domain-specific knowledge. The second is to balance the training process with the gradients or task weightages to avoid conflict between tasks. However, compared to single-task training that does not account for any task interference, the methods based on task weightage or gradient theory are not always more effective. To solve this problem, our approach, MPPS, is built on two ideas. First, masks are used to achieve the separation of shared networks between different tasks. Secondly, we adopt the idea of curriculum learning, learning from easy to hard. In our method, the number of shared parameters increases with the training process, and we introduced a new concept to help us describe this process mathematically. We use a concept named exclusive capacity or EC to describe the degree of parameter sharing. This concept is defined on the parameterized mask distribution, where we can calculate the probability as a continuous EC value. It should be noted that we set the probability to 1 on the task with the highest probability to avoid the situation where the neuron is not used by any task. And we define the EC value of a network as the average EC value across all shared neurons. It is obvious that the separated network has the highest EC value, and the shared backbone has the lowest EC value. A network with a higher EC value has a higher probability of processing task interference due to more shared parameters, and the network is also more difficult to train. Next, we illustrate the workflow of MPPS. MPPS is an iterative method. We first initialize the mask distribution with the highest EC value on a part of shared backbone, then sampling masks from the mask distribution for each task to build subnetworks, and doing forward propagation and back propagation on these subnetworks to update the shared parameters. We use the reinforce trick to estimate the gradient for updating the parameters of the mask distribution with a KL divergence term to encourage the current mask distribution close to a predefined target distribution. After we have updated the mask distribution, we obtain the target EC for the next iteration according to the EC scheduler, and change our target distribution using a rescaling method. This target distribution will be used to encourage the mask distribution to reduce its EC in the next iteration. We use average improvement compared with single-task training to indicate the effectiveness. CT indicates whether higher value is better or lower value is better. Here we show the performance of the MPPS method on 3 different benchmarks, and we can see that our method outperforms the benchmark method on all benchmarks. We implement MPPS with many SOTA methods, which includes task weightage methods, gradient theory methods, and different neural network designs. Our experiment results show that MPPS can work with most methods to achieve a better performance. And the MPPS would only introduce moderate additional training cost and no additional inference cost. That's all. Thank you.